In this video, we're going to learn how to find real roots by graphing. Now, sometimes you'll come across an equation that when you go to rewrite it to set it equal to 0, so I'll do this first by moving everything to one side, minus 4x squared, because I subtract it to the left, minus x plus 5. You'll get an equation that you may not be able to factor. In this case, you could try to factor by grouping, but you're not going to get a common factor, and we're kind of stuck at this impasse of what to do next. So what we can use is the graphing calculator, and what we do is plug this side in for one of my y's when I go to graph. So x to the third power minus 4x squared minus x plus 5. And I'll hit graph. And it'll give me a polynomial, but I'm going to look where that polynomial is equal to 0. I want to find zeros of the polynomial, so I'll use the 0 feature, which is located in second trace, the calculate menu. So second trace, the second option is 0. I'll hit enter, and then I'll go near one of the zeros, which seems to be around -1. And I'll go left bound, meaning I'll go left of the 0, hit enter. Then I'll go right of the 0 and hit enter. Then hit enter one more time to guess between those 2 points I picked. And I'll get first that x is equal to -1.094. And already I can see why this might have been hard to factor, because this doesn't even look like a fraction number. So it means that you probably get a radical, which already comes from quadratics that you cannot factor. But let's see what the other zeros are. To find the others, I'll do second trace, hit enter on 0, and right now it leaves off on the last 0 we had. So I'm going to go to the next one, and again, go left of it, so hit left a few times, go right of it, so there's the 0, go right some more, and hit enter one more time to guess that 0, and it said x is equal to 1.163. And the last 0 is located over here where it crosses the x-axis, so second trace, 0, shift this over to the last 0, again go left of it, then go right of the 0, hit enter, and it'll guess that x is equal to 3.931. Now be very careful not to pick a region like left of the leftmost 0 and right of the rightmost 0, because if you were to do this, left bound, I'm going to go all the way to the left, and then all the way to the right past the last one, it won't find all 3. It'll just find 1, seemingly at random. It looks like it found the rightmost one, but there were 2 other ones that we found earlier, so be very careful not to use it in that way. Now for the next example, I'll show you another method you can use to find all the solutions to an equation. Is you can look at each side of the equation as a different graph. So if I hit y equals, and I plug in x to the third plus x squared, and then x minus 1 into my other graph, where 2 equations equal or where they intersect. So I'll actually graph this and look for their intersections. So I have a line here that I see it crosses here, but maybe it crosses over there, but I can't tell. If I hit the zoom feature, I can zoom in. It gives me a little cursor, so I'm like, I'll zoom in around this spot to see if they intersect. So it goes up, and here's the line. I see they intersect here, but they don't intersect over there. So it's just one intersection. So what I'll do now is I'll go to the intersect feature, which is still located in the same menu. Second trace is the calculate menu, and the 5th option is intersect. Now the way this works is it picks a curve to start. If you want to switch between them, you hit up and down. But I'm going to start with the x cubed plus x squared, and you're going to move it near the 0, which is just behind this first curve thing over here. So I'm going to hit enter near where the intersection is, and it'll say second curve, which you see here, it just switched to the other curve. And again, I'm going to move the cursor near the intersection point, And I'm going to hit enter one more time, and it's going to guess the intersection was at x equals negative 1.839. So even though these were both like cubic equations, this one got 1 while the other one got 3. What that probably means is there's maybe 2 more solutions here, but they're imaginary solutions that we can only find by factoring, or maybe by using a different type of graph that can include imaginary solutions. Now let's look at a word problem with this. Second mode to quit. Now, close friends Stacy, Una, and Amir were all born on July 4th. Now, Stacy is 1 year younger than Una. Una is 2 years younger than Amir. And on July 4th, 2010, the product of their ages was 2,300 more than the sum of their ages. Now, how old was each friend on that day? July 4th, 2010. So the way we can do this is first we need to establish like what everyone's age is with a variable. So since we're comparing Amir and Stacy to Una, we'll let Una be x. So Una's age, let's say on July 4th, 2010, specifically. It's going to be x. Now, Stacy's age on that same day she is 1 year younger than Una, so it would be Una's age minus 1. And Amir's age on that same day is, since he is Una is 2 years younger than Amir, that means Amir is 2 years older than Una. So now let's take the statement here that the product of their ages was 2,300 more than the sum. So I'll write the product of their ages, which will be, all right, product, which would be x times x minus 1 times x plus 2, will be equal to the sum, which would be x plus x minus 1 plus x plus 2. That's the sum. And then the product was 2,300 more than the sum. So the sum plus 2,300. So now let me simplify this equation so I can solve it. So on the left, I'm going to multiply out x minus 1 and x plus 2. Give me x squared plus x minus 2. On the right, I'll add my like terms. So x plus x, which would be 3x. And then negative 1 plus 2, which would be plus 1. And that's plus 2,300. Again, distribute the x. X cubed plus x squared minus 2x equals 3x plus 2,301. And then I'll move everything to one side of my equation to solve. And again, I'm going to get a cubic polynomial that's going to be really hard, if not impossible, to factor. But it's equal to 0, so I can use that 0 feature to solve this. So I don't know how to factor this, so I will use my graphing calculator to graph x cubed plus x squared minus 5x minus 2,301. So x to the third plus x squared minus 5x minus 2,301. Now when I go to graph, I don't have a very good window. I'm actually still zoomed in from the problem before. So I need to pick a different window. One that preferably goes as low as 2,301, since that's the y-intercept. So negative 3,000. And it needs to reach at least 0 so I can find that solution. So I'll go up to like 100 or 1,000 past. So it has a nice range for the y's. x-wise, I don't quite know their age. I'll put a -5 so you have some leeway on the left for x. But on the right side, I'm going to go up to maybe up to 30 just to see how old they be. If I don't see a solution within that, they may be older than 30 years old for the age, at least for the Una's age. And the x scale, I'm going to count by 5s on my x's. And for y's, I'm going to count by 500s because it's such a big change. I'll hit graph, and I'm seeing here, here's my curve. And there's where it crosses the x-axis. That's the solution I'm looking for. So second trace, 0 feature. I'm going to go, there's the 0. I'm going to go left of it, hit enter. I'm going to go right of it, hit enter. Hit enter one more time to guess, and it's actually at x equals 13, which we'll learn some tricks later on in this chapter. But that means that this is factorable, but you have to use a different technique. So I know that x is equal to 13. So I'll put a little soft bubble around it. Doesn't answer the problem, but it does tell me at least 1/3 of the problem, which is Una's age would be 13. If I want Stacy's age, I'll do 13 minus 1, which is 12. And then Amir's age on that same day, July 4th, 2010, will be 13 plus 2, which is 15. So the one thing to be on the lookout for is while this feature is really nice for solving them quickly, it does leave out all imaginary solutions. So with word problems, it works out really nicely because sometimes we only want real solutions. But whenever you're just solving an equation, you might miss out on getting those imaginary solutions. And that is how you find real roots by graphing.